Okay, in this video we will be going over rules of differentiation and as well as giving some examples. Let's start with the simplest of functions. So we would like to take the derivative. There are basically two ways to write out the derivative, d over dx of, say, x to the power n. Or instead of being abstract, let's be more specific. For instance, we want to find the derivative of x to the fifth power. An alternative way to write this is x to the fifth prime. And the rule, whenever you have a polynomial expression like this, is to bring the exponent to the front and then reduce the power by 1. That's very straightforward. So here's another example, d over dx. Suppose that you want to take the derivative of 3x cubed. Well, which is the same thing as 3x cubed prime. All right. So, well, what can we do? Well, the 3 remains. Now, the x cubed part, when we take the derivative of the x cubed part, the 3 is the coefficient. That one just remains. Coefficients always, they just remain. Okay, x cubed, all we do is that power 3, we bring it to the front, and then we reduce the exponent by 1. So that's just 9x squared. Very straightforward. Here's another example. Say, for instance, that we want to find the derivative of 6x squared. I think the prime notation, as long as there's no confusion, it's easier than writing this expression d over dx, right? So this looks more cumbersome to write, right? So 6x squared, the 6 remains, the square on top of the exponent, so it just comes to the front as a coefficient, and we reduce the exponent by 1, so which is just 12x. X to the 1 is just x. Does that make sense? So that brings us to the idea of combining these. So how about, for instance, I want to find the derivative of, say, 6x cubed minus 3x squared plus, say, 10x minus 3. There you go. I want to find the derivative of this expression. Or let me just go ahead and write d over dx, so there's no confusion. So how do you do like combined expressions like this? The good news is the derivative is a linear operator. What that means is you can spread it. Does that make sense? So this is just gonna be spreading out. So basically the question then boils down to the following: 6x cubed prime, the derivative of that, minus 3x squared prime, the derivative of that part, the derivative of 10x, and finally the derivative of 3. All right, that should be easy now. So the derivative of 6x cubed is just keep the 6, multiply by 3, and square, minus. The 3 remains, bring down the 2, and then reduce the exponent by 1. All right, so it used to be 2, reduce it by 1, it goes down to 1. So then the 10 times 1, there's an invisible 1 here. That one is a prime, that one is a 1, right? So let me be more specific here. This one is a 1 versus this one is a prime. There you go. So the exponent, which is 1, comes down, and then x to the power 0. Now this is interesting because x to the 0 is just a 1. So finally, minus a constant, the prime of a constant, the derivative of a constant is always 0. So that as a result is 18x squared minus 6x plus 10. That's pretty much it. So that's the derivative of this big expression. So the good news is if you have these polynomial expressions, so in each of these cases our expressions look like this: a x to the power n. So the derivative of this expression is a times n times x to the n minus 1. So that's the key idea. So the a remains, the coefficients always remain, the exponent comes to the front, and x to the power, what's left is 1 less. Does that make sense? So this is how we handle polynomial expressions. So this is terms in a polynomial expression. All right. So next is, how about another common function type, which is, let's do trigonometric functions. A couple of examples of trigonometric functions. For instance, what is the derivative of sine of x? Well, this one turns out to be cosine of x. And how about the derivative of cosine of x? Well, that one is just sine of x. That's it. So very, very easy. Well, how about things like tangent of x? Well, we are not going to show it right now, but in just a minute when I introduce the quotient rule, you would remember that because tangent of x is the same thing as sine of x divided by cosine of x, all I will need is to apply the quotient rule to this sine of x divided by cosine of x, and it will come out very quickly. So I'll just say soon, in just a minute, as soon as I introduce the idea of the quotient rule. All right. But that's pretty much it. So for instance, you can spice things up a little bit, but for that, for instance, how about an expression like 3 sine square of x, the derivative of this. Now for that, again, I should say soon, only after I show you what's called as the product rule, as well as the, actually more than the product rule, I really need here the chain rule. All right, so both of these I'm about to show you just in a few minutes. All right, so that's pretty much the main results that you need to know. This one, the derivative of sine of x is cosine of x, and the derivative of cosine of x turns out to be, actually this is not true. The derivative of cosine of x is minus sine of x. My bad, sorry for that. It's minus sine of x. I'm sorry. There you go. Okay, so I hope this clarification was important, right? All right, so here's the next group of functions, which is exponential. So actually, maybe I should have written something, a note next to it. So the first type of examples were polynomial functions. The second type of functions were trigonometric functions. Trigonometric sine and cosine functions. And now we have examples from exponential functions. And all of these different function types have their own applications in not only finance, but in engineering and data science. There's a lot of applications. For instance, exponential function shows up prominently in the future value calculations, especially if the compounding is continuous. As an example, well, okay, so we can have a look at that later on. But okay, so how about the derivative of e to the power x prime? Well, it turns out e to the x is the only function whose derivative is itself, where e is the Euler number, which turns out to be 2.71 something. All right, so it is such a number. It's also known as the Euler number. It's arguably one of the most important numbers in the whole math. Another very celebrated number is pi, right? 3.1415 and so on. But just like pi, e is an especially important number, and that's one of the reasons why it's important, because e to the power x is the only function whose derivative is itself. All right, how about 2 to the power x? What's the derivative of that? It turns out the derivative of that is 2 to the x times ln 2. All right, so this is something that you guys can memorize if you want to, where ln is the natural logarithm. All right, where ln represents or denotes, represents the natural logarithm. What do we mean by natural logarithm? It means logarithm base e. Logarithms have base, and in this case it's logarithm base e, and that's pretty much it. So this is how you can differentiate exponential functions as well. Okay, with that said, let's quickly have a look at different rules of combining these. And we already discussed one of them. So whenever you have two functions, f of x plus, say, g of x, and you want to find the derivative of such an expression, it's very easy. All you do is you find the derivative of the first one plus the derivative of the second one. It can't be easier than that. For instance, if the question is asking for e to the x plus sine of x, and you want to find the derivative of this expression, all you need is the derivative of the first expression plus the derivative of the second expression. But the derivative of e to the x is just e to the x, plus the derivative of sine of x is just cosine of x. Does that make sense? All right, so that's the addition rule. But by that same token, so this is the second bullet. By that same token, you can also find a rule for the difference, and it is the same thing. F of x, you just take the derivative minus the derivative of g of x. Does that make sense? And let's give an example again. So example, so suppose for instance, well, 3x to the 10th power minus 2 to the x minus cosine of x. There you go. So you want to find the derivative of that. Very easy. All you do is 3x to the 10th power prime, the derivative of that, minus 2 to the x prime minus cosine of x prime, the derivative of each of these individual expressions. So 3 times x to the power 10, the 3 remains, the 10, and then x to the power, we reduce the exponent by 1, so it's x to the 9, minus 2 to the x, we already learned it's 2 to the x times ln 2, minus cosine of x, the derivative is minus sine of x. So as a result, the derivative of the desired expression is 30x to the 9 minus 2 to the x ln 2 plus, minus is a plus sine of x. There you go. So that's our second rule. So let me actually go ahead and highlight the rules. So this is how you can find the derivative of a sum of two functions. And this is how you would find the derivative of a difference of two functions. All right, you just take the individual derivatives of the functions and you subtract them. So it can't get easier. All right, so here's another one. So this one, we should be careful. It's something called the product rule. So what if we want to find the derivative of a product? Based on what we have so far, some of you guys might be inclined to say that the answer is just take the derivative of the first one and then multiply it with the derivative of the second one. But that would be false. Nope. So there's an actual rule which is called the product rule. So the product rule says the following. So let me rewrite that. So it's just if you have two functions, f of x and g of x, and you multiply them and you want to take their derivative, what you can do is you can take the derivative of the first one, which is f of x, so f prime of x, multiply it with the second function, plus the derivative of the second function times the first function. Does that make sense? So that would be the product rule. Let me go ahead and again provide an example. Suppose that we want to find the derivative of e to the x times, times, why not, ln x. So this is a product. Well, actually, you know, I don't think I mentioned ln x. I should have when I was talking about the exponential function. So let me go ahead and insert it over here, all right? So it's actually a very simple rule. The derivative of ln of x turns out to be just 1 over x. That's it. It can't be easier. What if it's not the natural logarithm? What if it's just the logarithm base 10 or another base, right? Base 10 of x. All right, so for this one as well, there is, well, it turns out that there is this very neat idea that we can actually split this. We can split it as ln of x. This is one of the properties of the logarithm function divided by ln of 10. But ln of 10 is just a constant, so that's just, we can keep the ln of 10. Sorry, we're still trying to take the derivative of this expression, right? I shouldn't forget that. Okay, and then ln of x. So we want to take the derivative of this expression. But we just said that the derivative of ln of x is just 1 over x. So we will still have the 1 over ln 10. And now we also have the 1 over x. Now, we can't apply the product rule here because this is just a number, a constant, which will come out of the derivative sign, right? So I hope that makes sense. All right, so in this case, now we can apply the product rule because this is a function which has, in terms of x, this is another function in terms of x. You can think of this as f of x and g of x. If they are multiplied and we want to find the derivative, easy. The rule says take the derivative of the first one, which is itself, e to the x is the only function whose derivative is itself, times the second function, plus the derivative of the second function, which we just said is 1 over x, times the first function. And that is pretty much it. So that would be the product rule indeed. So let me just go ahead and highlight this rule as well. This is the correct rule, not the one above it, right? So the line above that, that would be incorrect. So this is one of the things that you should be careful about when you take the derivative of a product of two functions. All right, so finally, last rule is the quotient rule. So what if we want to find the derivative of a quotient like this? Is it going to be equal to f prime of x divided by g of prime of x? The answer is no. That's not what the quotient rule is. Quotient rule, just like the product rule, has a different thing, and here it is. So this is just it turns out to be, we draw a long division sign, g of x squared in the denominator, and in the numerator will go like this: the derivative of the first function times the second function minus, now this one was a plus, remember that one is a minus, the derivative of the denominator times the numerator, just the function itself. And that's pretty much it. So this is the quotient rule, the correct rule. Maybe I should go ahead and highlight this as well. So those are our most common rules that we use. Actually, this is pretty much all the rules that we use in calculus, basically. That's it, when we take derivatives. All right, so as an example, finally, let's give an example to this one. Suppose that we want to find the derivative of, say, 5x cubed divided by sine of x. We want to find derivative of that. Should be pretty easy. In the denominator, we'll just square the denominator, sine square of x. In the numerator, we'll take the derivative of the first one, 5x cubed. The derivative would be 15x squared multiplied by the denominator, the function in the denominator, minus the derivative of the function in the denominator, which is cosine of x, times the numerator, 5x cubed. And that's pretty much it. So this would be the desired result. So obviously, if you want, you can try to factor out the numerator, but that shouldn't be too hard. So you guys can try it out on your own, or yeah, okay, let me just do it, I guess. There's a common 5 here. There's also common x squared, so 5x squared can be factored out. We already have a denominator of sine square of x. So what's left in the numerator will be a 3 here in the first term, and then a sine x, 3 sine of x. And then in the second term, we have cosine of x and x, minus x times cosine of x. That's pretty much it. So that would do this example as well. So let me just go ahead and go all the way up to the page. So what we did so far is we looked at different function families. We first started with the polynomial functions, and we learned how to take the derivative of polynomial functions, and the rule was very straightforward. All you do is, if there's a coefficient in the front, just keep it in the front, and then the exponent comes to the front, multiplied with whatever coefficient is already there, and then the exponent goes down by 1. And we did numerous examples, as you can see here. Next family of functions that we looked at were trigonometric functions, and we already gave you the example of sine of x, the derivative of sine of x, and cosine of x. Initially, I forgot the minus sign here, but later on, I realized that cosine of x, its derivative as a minus. Now that we finished all this so far, actually, let's quickly also solve these two, which we skipped earlier, right? Actually, this one we can, but this one, for the second one, we'll need to learn one more rule, which I will show next. But sine of x divided by cosine of x, we can apply the quotient rule, which is, for the denominator, we will just go ahead and square it. But for the numerator, take the derivative of the numerator, sine of x, the derivative is cosine of x, multiplied with the denominator, which is also cosine of x, minus derivative of the denominator, derivative of cosine of x is minus sine of x, multiplied with the numerator, which is sine of x. So finally, this will come out as cosine square of x minus minus, so which is plus sine square of x. But cosine square of x plus sine square of x divided by cosine square of x. If you remember from your pre-calculus courses, cosine square of x plus sine square of x is just a 1. So this whole thing boils down to 1 over cosine square of x. So that's the derivative of tangent of x. Awesome. So now we still need to work on the last one, but only after we learn something called the quotient rule. In just a minute, quotient rule. All right, so we did the trigonometric type of functions. Next, oops, wait. Next, oh, how did I manage to do that? Okay, so you guys can totally ignore what I just did here. Well, how do you guys ignore it? Oh, there we go. All right. Let's just get rid of that. All right, so the next family of functions were exponential functions. And what we did is I showed you guys some rules. Basically, the exponential function e to the power x, the derivative is itself. 2 to the power x or any other number raised to the power x is 2 to the x times ln 2. For instance, how about the derivative of a to the power x, where a is a number? It's just, again, a to the x times ln a, right? So very straightforward. Next, we also looked at the logarithm function, ln of x. The derivative of ln of x is 1 over x. And then the derivative of any base, logarithm, say base 10 of x, we can use this following trick where ln x divided by ln 10, and then we can split it as 1 over ln 10 times ln x. The derivative of that, because 1 over ln 10 is just a number, we just carry it, and the derivative of ln x, we just mentioned it here, it's 1 over x, so that's it. So that would be the answer. Lastly, we started looking at the rules. First, we looked at the addition rule. Addition, how do you find the derivative of two functions which are added? How do you find the difference, right? So the difference, the derivative of a difference of two functions. Then we looked at the derivative of a product of functions, product of two functions. How do you find their derivative? And then we looked at the quotient, the quotient. How do you find the derivative of two functions which is divided to each other? Again, we learned it. The last, very last rule remaining is the chain rule. And it turns out to be probably one of the most useful rules you will ever see and you will always use. And it is the following. So if you have the derivative of a composition of functions, how do you accomplish that? Well, it turns out that it will end up being this: f prime of g of x times g prime of x times. So what that means is you just take the derivative of the inside function, which is here, and then you take the derivative of the outside, so f prime. However, you plug in f g of x. This form is not very useful, one might say. A better, more useful way would be the following. We can just consider, suppose that d of, dy over dx. With this notation, I think it will be clearer. What the chain rule says is the following: dy over, say, for instance, dz times dz over dx. So this is kind of the main idea, or if you want, let's just use the same functions, right? So let me just remove these instead of, so let's say df over dx is simply df over dg times dg over dx. That's what it is. So here, this part is the f prime part. This prime is the g prime part. We are multiplying them. This one is g prime of x. This one is f prime of g of x. I hope that's clear. And that's f of, this is the overall function, right? F of g of x. We are taking the derivative of this thing. All right, so that would be the chain rule. Let's solve a couple of examples. What if the question is asking for ln cosine of x? How do you find the derivative of this expression? Oops, let's just rewrite this better. Cosine of x. So this would be an example. Let's solve multiple examples related to this subject because it's somewhat important. So the derivative is the following. It's as if the function outside, this is the f function, and this is the inside one, this is the g function. So the rule says always take the derivative of the inside. So we will need to take the derivative of the inside, so this part, and then multiply with what's remaining, ln of just basic, so now we can take the derivative of ln function, the outside, right, and then plug in the cosine x again. So the derivative of ln was 1 over x, remember? So but instead of writing x, we need to write the actual function. Do you guys see that? 1 over cosine of x. Does that make sense? So it was I thought it was relatively straightforward, right? So and that's it. So cosine of x, the derivative is minus sine of x, and we still have 1 over cosine of x there. Or if you want, we can write it as minus sine of x over cosine of x, but sine of x over cosine of x was tangent of x, so this is minus tangent of x. Very straightforward. So here's another example. Say, for instance, you want to take the derivative of 6x cubed minus 10x square. So you want to take the derivative of this expression. This time it's as if the outside function is the square function, the x square if you want, and this is the inside function. Do you guys see that? So we'll just take the inside, the derivative of the inside, which is, let me do it in 2 steps, minus 10x. We'll take the derivative of that times, and then for that remaining piece, we will take the derivative. The derivative of x squared is just 2x, so 2 times. But instead of x, we will write the whole thing, right? So the whole inside. 6x cubed minus 10x. Yeah, I hope that's clear. And now the rest is pretty straightforward. So this would be equal to, so the derivative of this expression is just 6 times 3, which is 18x squared minus 10. We still have a 2. And then the rest. Actually, let me go ahead and factorize this expression. So I can factor out an x and then a 2. So that will be 2x. After factoring out the 2x, what we will be left with 3x squared minus 5. But then I just realized in this first expression, we can also factor out another 2. So we have a 2 from this one. Actually, let's do it in 2 steps. 2 times 9x squared minus 5 times 2 times 2x. So that would be 4x. And then we have 3x squared minus 5. Finally, in a factorized form, so 2 and the 4, 8x. And then we have 9x squared minus 5. And then 3x squared minus 5. That's it. That would be the derivative of this initial given expression. Maybe I can just make my handwriting better. X squared minus 5. Let's do one last example, I guess, so that we just wrap up this topic. So this time we did use an example of trigonometric function, logarithm, exponential. I guess, yeah, so we can continue doing something similar. How about I do the derivative of e to the power x squared minus 3x. So we want to find the derivative of this expression. Again, this function, it's as if is embedded inside the function e to the x. So what I'm going to do is I'm going to first take the derivative of the exponent, which is, okay, let's do it in 2 steps. There you go. And then the derivative of e to the x was still e to the x, so I'll just leave the expression as it is. And finally, the derivative of this coefficient here, well, yes, so it would be derivative of x squared is just 2x. And then derivative of minus 3x is just minus 3 times e to the power x squared minus 3x. That is it. So that would be very, I mean, yeah, so that we can obviously come up with more complicated functional forms, but that would do, I think, for the time being. So this is how you would basically take the derivative of a function. That was the last rule that we learned, the chain rule. So in the next lecture, let's continue with a couple more examples, and also I would like to provide 1 or 2 more interesting cases, how to handle those cases, especially the situation with partial differentiation. So what happens if a function is a multivariate function? Instead of 1 input, it has 2 inputs. How do you take the derivative then? All right, so see you then.